I make the announcement so that when I put it on the YouTubes, people can see it. All right, so first of all, last homework, still due on Friday. I've had 3 weeks now to work on it, so due the usual time on Friday. Final is due next week on Tuesday, I believe, June 11th. At 6 p.m., I believe. The other thing I wanted to say is this is the last week of the quarter, right? So hardly any more classes left. Your last homework is due on Friday, and things have been going faster than usual. And hence, what we're going to do is on Friday, no class. All right, so Wednesday is going to be our last lecture. It'll be fascinating, I assure you, as it always is. And then Friday, you'll have the day off, at least as far as statistical mechanics is concerned, and get your homework in, and that'll be it. All right? All right, cool. All right, so with that, then let us do our thing, unless you guys have any questions or anything you want to say. Negative. All right, so then let me fire up the old iPad here. There it is. All right, beautiful. All right, so on Friday, where we left off was we were solving the general Ising model in one dimension. Okay, and what we mean by general is that both the interaction parameter and the external field, which, so now we're going to talk about this a little bit more today. And so I've been indicating the external field by B. Sometimes that can get a little confusing, might get mixed up a little bit with beta. And so I may periodically in my notes, and while I'm working things out here, I may also refer to it as H, okay? But same thing, all right? It's just the external field. And then depending on primarily what I've got written in my notes here as I try to explain it to you, I may accidentally throw an H in there. So if I say H, what all H is just the external applied magnetic field, okay? So in general, for the generalizing model, both the external field and the interaction parameter are not zero, okay? And hence, our Hamiltonian looks like this. So it's the sum over nearest neighbors of our spin parameter minus our dipole magnetic moment magnitude times the external field times the sum over each individual spin. All right, so now what we showed on Friday was that the easiest or most direct way to solve this general problem is to cast it in terms of matrices. All right, and so we defined a matrix that we called P that has, it's a 2x2 matrix, so it has where its indices are labeled by our spins, and the elements of this matrix are equal to e to the beta j sigma 1 sigma 2 plus mu b over 2 sigma 1 plus mu b over 2 sigma 2. So those are the matrix elements. So you just plug in your various values of sigma 1 and sigma 2, and that'll tell you the what each element of the matrix is. And so what you get is that this matrix, if you write it out, looks like this: e to the beta j plus mu b, e to the minus beta j, e to the minus beta j, e to the beta j minus mu b. Okay, so that is our matrix, P. Okay, so now what we showed on Friday was that if I have a system of n spins, and I wanted to calculate the partition function of that system of n spins, then all I have to do is to take this matrix P, raise it to the nth power, where again, n is the number of spins. So if you've got 3 spins, then n would be equal to 3, so on. So in general, we have n. Hi, Min. All right, so we have
Hello.
this. Hello.
Sorry, I
Okay.
joined late. I
Oh,
need
that's
to unmute myself
yes,
or mute
please.
myself.
Yes. All right, cool. Okay, so we have this matrix P raised to the nth power. And then to get the partition function out of this, what we do is we take the trace. Okay, so the trace of this product of n matrices, as we showed on Friday, is equal to our partition function for a system of n spins. Okay, and again, the trace, if I have a matrix A, the trace is just defined to be the sum along the diagonal, like so. Okay, so I just set the two indices equal to each other and then just sum along the diagonal. Okay, now what we showed is that this right here allows us to solve this problem in general through some pretty useful properties of the trace, all right? And the properties of this P matrix. So this P matrix, if you look at it, so first of all, it's real, right? There are no imaginary components, so it's real. And it is also symmetric. Okay, and what that means is that your off diagonal elements, this one and this one, are the same. Okay, so the fact that they're the same means that it's symmetric. And it turns out that any real symmetric matrix can be diagonalized. Okay, through techniques which you presumably learned in quantum mechanics. Okay, so in general, your matrix P is related to its corresponding diagonal matrix by a similarity transformation where you multiply D by another matrix called U, where U is a unitary matrix. Okay, and the definition of unitary is that U times U transpose is equal to U transpose times U is equal to the identity. That's an awful looking one. The identity matrix, there it is. Okay, so now what that means is that you can always take a matrix like P and find and diagonalize it to yield a matrix D. And this matrix D in particular, so again, it's diagonal. So it's only going to have elements along the diagonal. Everything else is 0. And in particular, these diagonal elements are the eigenvalues of P, which we call lambda plus and lambda minus. So here, lambda plus and lambda minus are the eigenvalues of P. Okay, now, so now when you take the trace, so what we're interested in is the trace of P to the n. So first of all, we just focus on the trace of P. This would be the same thing as the trace of U D U transpose by definition. And another useful property of the trace is that it is invariant under cyclic permutations of its argument. Okay, and what that means is that this is the same as if I, again, cyclically transpose these matrices. So I get this. That's U transpose times U. So that's just, I'm just, shifting them all this way, and then this guy goes to the front. And then this, essentially by definition, the fact that it's a unitary matrix, this gives you 1. And hence you get that the trace of P is equal to the trace of D. All right. So in other words, and so that now is very simple because we know D is diagonal, so that means we just add up our eigenvalues. This is just lambda plus lambda minus. All right, but now we're not interested in the trace of P, we're interested in the trace of P to the n. Like so. But now again, what we showed on Friday was that P to the n, you can write out as a long string of these similarity transformations. So we'll have n factors of this similarity transformation, du transpose, where there's n terms of these. Okay, and again, the fact that u transpose u gives you 1, then what you wind up with is that the p to the n is just a similarity transformation of d to the n. Like so. Okay, and so now, again, if you take the trace of this thing, then again, you can do this trick with the cyclic permutation of the argument of the trace. And so again, what you wind up with is that this is just the trace of d to the n. Okay, and d to the n, because d is such a nice straightforward matrix, it's diagonal. You just take it and raise it to the nth power. And again, because it's diagonal, calculating this thing is trivial. It's just lambda plus to the n, lambda minus to the n. Okay, and so now when you take the trace of this, again, it's just the sum of the eigenvalues raised to the nth power. And this is, again, because this is true, that means this trace of d to the n is going to be equal to the trace of p to the n. And the trace of p to the n is our partition function. Okay, so the partition function is simply the sum of the eigenvalues of p raised to the nth power. So in other words, this relatively complex problem, we have reduced in simplicity to now all we have to do is take this 2x2 matrix that we defined right here, this guy, and all we have to do is find its eigenvalues. Piece of cake, we know how to do that. Okay, so you find the eigenvalues of this simple 2x2 matrix, you raise them to the nth power, and then you add them up. That's your partition function, and you're done. And then again, once you've got your partition function, you're a god, right? You've become a god, and you can tell everything that you ever wanted to know about this problem. Okay, so all we have to do is find the eigenvalues of p. Piece of cake, okay? And so again, you guys have all done this in quantum mechanics. You know how to find eigenvalues of any matrix, okay? And so I'm gonna skip all the tedious algebra and just tell you what the answer is. And I already told you what the answer was on Friday. I'm just gonna tell you again. All right, so the eigenvalues of p, there's two of them labeled by plus and minus. They are equal to e to the beta j times the hyperbolic cosine beta mu b plus or minus the squared hyperbolic sine of beta mu b plus e to the minus 4 beta j square root. There it is. And again, so the eigenvalues look exactly the same. The only difference between them is for the plus eigenvalue, you take the plus sign, because what you wind up doing here is solving a quadratic equation. That's where this comes from. So the plus eigenvalue is the one that corresponds to taking the plus solution, and the minus eigenvalue is the one that corresponds to taking the minus solution. Piece of cake. Okay, so that's it. So now we have our eigenvalues. So now let's write down our partition function. So our partition function, Zn, is just lambda plus to the n plus lambda minus to the n. And so if we write that down, it's simply e to the n beta j times this thing that we just wrote out, cosh beta mu b plus sinh squared beta mu b plus e to the minus 4 beta j raised to the nth power plus, and let me make my life easier here. I'm going to add another bracket there. And then it's just the same thing, cosh beta mu b minus sinh squared beta mu b plus e to the minus 4 beta j raised to the nth power. And then both of those terms are times e to the n beta j. So there's our partition function. That's not, well, I mean, it's not pretty by any means, but it's not so awful, right? I mean, that's doable. We can work with this thing. Okay, and so now what we want to do, so that's our partition function, right? And so now once you know the partition function, you just follow the general rules. You take the logarithm of this thing, which gives you the free energy, and then you start computing derivatives of the free energy in order to determine expectation values. All right, so now in particular, the expectation values we are interested in. So let's now compute. We're interested in the magnetization, M, and the magnetic susceptibility, chi M. Okay, so now what we have to do is take derivatives of this. Well, first we take the logarithm, then we take derivatives, okay? It's going to be kind of a mess, right? A logarithm, that is not a pretty expression. You take the logarithm of that, that makes it even less pretty expression. And so it's going to start getting a little hairy. Okay, but we can simplify this a little bit by making an approximation. So what approximation are we going to make? We're going to make our usual approximation in statistical mechanics, and that is we are looking at a crap load of electrons. Okay, so in other words, in the limit where n is very, very big, that is, it heads towards infinity. Okay, then let's have a look at these eigenvalues. Okay, so let's actually look right here. So we have two terms. This term here corresponds to lambda plus. Okay, so we got lambda plus raised to the nth power. And this term right here is lambda minus raised to the nth power. Now notice that lambda plus has this plus sign in it, hence the name. And lambda minus has a minus sign in it, hence the name. And what that means, so now again, all these quantities are real, and in general, they're going to be positive. Okay, now what that means is that because what you're doing here with lambda plus is I shouldn't use red. What you're doing with lambda plus is adding two things together. And with lambda minus, you are subtracting two things that in general, lambda plus is going to be bigger than lambda minus, right? So in general, lambda plus is bigger than lambda minus, okay? So you take a number, raise it to the nth power, and you take another number and you raise it to the nth power. That's going to make them even bigger, right? And even if lambda plus is even just a tiny, tiny bit bigger than lambda minus, as you take that to the nth power and n gets very, very large, then what's going to happen is going to be the difference between them is going to get bigger and bigger and bigger. Okay, so in other words, as n gets very large, lambda plus, because it's bigger than lambda minus, is eventually going to just completely overwhelm lambda minus. Okay, so in the limit where n goes to infinity, and this is true, then lambda plus to the n is going to be much, much bigger than lambda minus to the n. In other words, we're just going to forget lambda minus, all right? Okay, so what that means is that in this limit, log z to the n is approximately equal to just the log of lambda plus to the n. okay, because we're just going to neglect lambda minus because it's going to get swamped out by lambda plus because n is so large. And this is n log lambda plus. Okay, now okay, let me go ahead and write it out just to be thorough. So it's n log e to the beta j times cosh beta mu b plus sinh squared beta mu b plus e to the minus 4 beta j square root. There it is. Okay, so it's even less bad. I'm still not going to say that it's good, but it's less bad. So now this is, tractable. We can work with this thing. All right. So now this is the logarithm of our partition function. The free energy is defined to be negative 1 over beta log of the partition. So in other words, it's essentially this thing times a constant. And so now what we want to do is start taking derivatives of this thing, right? So for example, the average energy, which is the average of the Hamiltonian, is minus d beta log z. Okay, the magnetization, as we've shown before, is minus d phi d mu b. And the magnetic susceptibility is 1 over n dm d mu b, I believe is what we came up with. Okay, so we have this thing. Now our job is to do these things. Okay, and again, it's relatively straightforward. You just, it's just an exercise in taking derivatives. And so again, I'm just going to give you the answer. I'm not gonna wade through exactly how you do all this because it's just an exercise in derivatives. So in particular, we are curious about the magnetization, right? So the magnetization is a function of the applied external field and the temperature. And the way that you get it is you take your free energy and you differentiate with respect to mu b. All right, and what you will get if you do this is sinh beta mu b over sinh squared beta mu b plus e to the minus 4 beta j to the 1/2. All right, so that's it. That's the magnetization. All right, so now this thing is, we got an expression. It's, it's not that intuitive as to exactly what it means, okay? And so what I'm going to do is just draw for you what it looks like at various values of these parameters. Okay, so for example, if we draw the magnetization as a function of mu b, okay? And so now, so in other words, the x-axis is this thing that's in the numerator and denominator, but you can see we've still got this other parameter j. Okay, so in principle, I can draw this curve for different values of j, but I'm gonna pick one just to make it, readable. So all these curves I'm gonna draw are for j equals 1. Okay, and so now what I'm gonna do is draw it for different temperatures. So you can see the temperature enters here in beta. Okay, so first of all, let's draw it for really cold temperatures. All right, so for really cold temperatures, the maximum value of this, I think I missed a factor of n somewhere. I think there should be an n out here. So anyway, the maximum value of this thing is n. Okay, and at 0 temperature, what this thing does is it starts at magnetization equals 0. And as you crank up the field, it essentially immediately jumps up here to n. And then it does this. So it's essentially a step function. Okay, and the way that you can think about this is that, again, what's happening is all the spins are interacting with one another. They're trying to make each other align with one another. But without any applied external field, then the problem is that the problem has essentially like rotational symmetry, right? There's no preferred direction that any individual spin wants to go just based on the external circumstances of the material. And so hence what happens is all the spins essentially fight each other out and everything cancels out to zero. But as soon as you apply an external magnetic field, what you're doing is you're breaking the symmetry of the space. You're essentially defining a preferred direction in space that is the same direction as the field, and everything just instantaneously, bam, aligns in the direction of that field. And so you get a step function like so. Okay, so this is for zero temperature. And so now what happens as you ramp up the temperature is, again, the temperature corresponds to random thermal fluctuations of these spins. And so what this does is you ramp up the temperatures, it essentially just smears out this step function. Okay, so let's see, Roy G Bis. So green would be next. So what happens is as you increase the temperature, this thing just gets smoother and smoother. So this would be another temperature, so we'll say this is KT equals 1. Roy, okay, then as you make the temperature even higher, it does this. It's even smoother. It's KT equals 2. KT equals 3, nice and smooth. And as it gets hotter and hotter, it just gets smoother and smoother. Okay, and again, what that corresponds to is temperature goes up, thermal fluctuations go up, and essentially the thermal fluctuations, as it gets hotter and hotter, are able to overcome the spin-spin interactions, and hence it takes a stronger field in order to get everything to perfectly line up. Okay, so that's what it looks. So that doesn't look very different than what we had previously. It looks pretty similar to what we had before. I can also plot what this looks like. So now, again, on the y-axis, I'm going to plot the magnetization, and on this axis, I'm going to plot KT. Okay. Now, okay, so what we have, so now I'm going to plot for different values of the magnetic field. Okay, so again, as you increase the temperature, what's going to happen is you'll start out with, so here, let me first of all draw it for a low magnetic field. So this is B approximately equal to 0, but not quite, because again, if it were equal to 0, you'd have no magnetization. So we've got a little weak, tiny field. And that will give us a magnetization, again, equal to N. So now if the external magnetic field is very weak, as you crank up the temperature, that thermal fluctuations are very quickly going to overwhelm the alignment caused by the external magnetic field. And so what you're going to get is it'll start at N and then very quickly decay down to 0, like so. And again, then what happens as you ramp up the field is it becomes more and more resistant to the temperature. Okay, so for example, you make the field a little bit stronger, and it'll kind of do this before it decays. So this is that's for a higher B. You crank it up a little bit higher, and it's going to be able to hold out longer and longer. So you get the idea. So this way is increasing B. All right, so that's the way this thing behaves, which again, it makes rather intuitive sense when you think of it as a competition between spin-spin interactions and thermal fluctuations coming from temperature. All right, so we did it, right? We solved why magnets work, right? So magnets work as a consequence of spin-spin interactions. except we haven't, right? We haven't explained how magnets work. Why have we not explained why magnets work? Well, it's because of this right here. All right, and in fact, if you go back here to this expression that we have for the magnetization, what happens? So here's the magnetic field in the numerator. And what happens when you apply 0 external magnetic field is sinh of 0 is 0, and hence there is no magnetization. Okay, so now the problem with this, problem is, magnets are magnets. They have a magnetic field, they have a magnetization, even in the absence of an applied external magnetic field. So magnets have spontaneous magnetization. Okay, what that means is that the magnetic field, the magnetization at 0 applied magnetic field and finite temperature is not equal to 0 in order to have a magnet. But now the problem is this thing is equal to 0. Okay, the problem is that the magnetization of the Ising model in one dimension at 0 external field is 0. Okay, so in other words, this does not explain magnets. Okay, so sad. Tears. Okay, there it is. We're very sad because we worked through all this and damn it, we still don't have a handle on magnets. Okay, and so now the problem is that, again, we've already talked about this. In one dimension, the Ising model does not exhibit phase transitions. So the 1D Ising model does not exhibit phase transitions. Okay, and as I'm about to show you, in order to get a spontaneous magnetization, you have to be able to get a phase transition in your model. Okay, so now why is that? So let's talk about that. So let's talk about phase transitions in general and how they apply to magnetism. Okay, so again, a magnet, like a refrigerator magnet that sticks onto your refrigerator, has non-zero spontaneous magnetization. Okay, so even with B equals 0, a refrigerator magnet, for example, has M of B equals 0 not equal to 0. That's what makes it a magnet. Okay, so in general, a magnet, well, I wrote it right here. So in general, that's going to be true for any actual magnet. Okay, so now let's think about how the magnetization behaves, specifically as a function of temperature. Okay, so for a magnet, you expect something that looks like the following. All right, so let me plot, again, magnetization on the y-axis, and I'm going to plot temperature on the x-axis. And so now you guys, so again, intuitively what's happening here is that at low temperatures, the spin-spin interactions are strong enough to essentially drive the alignment of spins over macroscopic scales in the material, such that when you add up the spins of all the electrons in the material, they, all generally point in some direction, and that gives you a net magnetization. Okay, so in other words, at low temperatures, you start out, let me use a different color just because I like it, it's pretty. So you start out at some non-zero magnetization. And again, that's because the spins are all aligned due to spin-spin interactions. And as you ramp up the temperature, that increases the thermal fluctuations. And at some point, the temperature is high enough that even though they're, attracted to each other, the random thermal fluctuations are enough to overcome the spin-spin interactions. And so what's going to happen is that you're going to hit some temperature where you see no more magnetization. All right. So in other words, what we expect and what you observe experimentally, if you measure the magnetization of a magnet, it behaves like this. It goes, okay. And at some temperature right here, the magnetization hits 0. And as you increase the temperature beyond that, it stays 0. All right, so this is what our magnetization curve looks like. The temperature at which the magnetization goes to 0 is what's called the Curie temperature. All right, so the Curie temperature is the temperature where the magnetization, spontaneous magnetization, drops to 0. And so now, if you look at this plot and you think about what this means, this is telling you that what you're observing here is a phase transition. All right, and so on the left side of this plot, again, what you have is an ordered state, and that ordered state corresponds to the spin-spin interactions driving alignment of the spins in the material to all point in generally the same direction. Okay, so this is an orderly spin-aligned region. Okay, and then once you cross the Curie temperature, the thermal fluctuations take over, and so now this is a disordered state. Okay, so this is a more or less, well, as we'll show you in a second, it's not exactly analogous to water, but it's very similar to water in that below some temperature, the hydrogen bonding of water molecules drives them into an ordered regular state that corresponds to ice. And as you increase the temperature, the thermal fluctuations of the water molecules eventually overwhelm those hydrogen bonds, and it makes a transition into a disordered state, that is liquid water. Okay, so at this temperature, you undergo a phase transition. Okay, and now it turns out that in statistical mechanics, phase transitions arise from very specific features. Okay, and what I mean by that is that when you look at the free energy, that in order to get a phase transition, what you need is some sort of singular or pathological behavior in the free energy. Okay, so phase transitions arise from singular or pathological, and I'll tell you what this means in a second, behavior of the free energy. And remember, that's this thing we called phi, the logarithm of the partition function. All right, so now to understand what I mean by this, let's think about the phase transition that I think we're probably all the most familiar with, and that is water going, melting. Okay, so consider water as you heat it. Okay, so imagine you have a block of ice and you apply heat to it. Okay, so I throw in some heat energy Q. Okay, and then you guys know what happens. So this is at some initial temperature T naught. What happens as I put heat energy into this thing is that I raise the temperature of the ice. So the first thing that happens is that I raise the temperature of the ice according to this. Q is equal to mc delta T. So the amount of heat energy I put in corresponds to some change in temperature. Okay, so and now from the first law of thermodynamics. So the first law of thermodynamics is that the energy of the ice is equal to the heat that you put in. I guess in principle I should do this in differential form, minus the amount of work that is done. So now as we heat this thing up, we are not doing any work, right? So in other words, we don't have to worry about this. So in other words, the heat that we put in corresponds to exactly to changes in internal energy of the ice. All right, so now let's plot what happens. Okay, so I'm going to plot the internal energy of the ice here on the y-axis, and I'm going to plot the temperature of the ice on the x-axis. And so now what happens is that I start out at some initial temperature, that's right here, that corresponds to some initial energy. And as I put in heat, that raises the temperature and correspondingly raises the energy. Okay, and this is the equation of a line, right? So this is the internal energy of the ice. As I add energy, as I increase the temperature, I increase the energy linearly. Okay, so in other words, I start here, and as I add more energy, as I increase the temperature, the energy goes up like so, until we get to the melting temperature. Okay, so the first thing that happens is our block of ice heats up from T naught to T melting. Okay, now the next thing that happens is we keep putting heat in. Okay, but now what happens is as you put heat in, the temperature does not change. What happens is that the heat energy goes into breaking the hydrogen bonds between the different water molecules. And so the amount of energy of the ice goes up by this, the heat of fusion of the ice. Okay, but you'll notice that it doesn't have any T in it, right? So as you break the hydrogen bonds, the temperature does not go up, but the internal energy of the ice does. Okay, so at the melting temperature, we're going to add more energy. So in other words, what happens is that this thing jumps straight up to here. I should get rid of this, like so. Okay, and so what happens is that at the melting temperature, we have melted our ice into a puddle of water. And this is still at the melting temperature. And then as we add more energy into it, it's going to heat up again. Okay, so at the melting temperature, we get a discontinuity in the internal energy. And then as we start adding heat energy again, the temperature starts increasing. Okay, so the key point here is that this phase change is observable in this diagram as a discontinuity. So the phase change is a discontinuity in the internal energy, E. Okay, does that make sense? Okay, so now it turns out that all phase changes are like this. So this is what I mean by pathological behavior, is discontinuities, okay? So if you have a phase change in some plot like this, you are going to see a discontinuity somewhere, okay? So now, here we see, for this case of ice melting, our discontinuity shows up in the internal energy of the ice. All right, so now the internal energy, as we've talked about repeatedly now at this point, the internal energy is just the average of the Hamiltonian. All right, and the average of the Hamiltonian, we've shown this before, is related to a first derivative of the free energy. So the free energy is this log z thing. Okay, so this is the free energy, essentially, up to a constant. And so we take one derivative to get our free energy, not our free energy, our internal energy, and then there is a discontinuity here. Okay, and the fact that the discontinuity shows up in the first derivative of the free energy means that this is what is referred to as a first order phase transition. Okay, so a first order phase transition is where a discontinuity shows up in the first derivative of the free energy. Now, again, this thing is essentially the free energy. And so now in order to get a discontinuity in the derivative of the free energy, what that means that the free energy must look like. So the free energy as a function of temperature, what that means is that somewhere in the free energy, there has to be a kink. Okay, so something that looks like this. And then it hits this point, and then there's a sudden abrupt change to a different slope. Okay, because again, the derivative tells you the slope of a function. And the fact that there's a discontinuity in the slope means that your function has to have a kink in it somewhere, like this, at some specific temperature. Okay, everybody cool? All right, so that's ice. That's how so the transition from ice to water is a first order phase transition because there is a discontinuity in the internal energy of the ice across that phase boundary. So now let's think about magnetization. So back to magnetization. All right, so now I've already showed you a function that describes magnetization that has a kink in it, right? So we already drew this. We showed that as you increase the temperature of your magnet and you plot the magnetization of your magnet, that what you get is a function that looks like this. So it starts out at some value, and then as you heat it up, pow, kink. Okay, so that means that the derivative of this is where the discontinuity is going to show up, right? Okay, but now, the magnetization, we showed you, for example, so the easiest place to see this is for our zero interaction model. If you go back to the zero interaction model, you get we showed that the magnetization is just proportional to the energy, right? So the magnetization is just the energy divided by, so I have in my notes here, H. So again, the field. So whether that's B or mu B, it's one of those. So in other words, the magnetization and the internal energy are directly proportional to one another. But now the internal energy is already the first derivative of related to the first derivative of the free energy. Okay, so now we take the first derivative of our free energy and we don't yet have a discontinuity, right? It's this function that has the kink in it. So it's only when you take the derivative of this function. Okay, so now if we take the derivative of the magnetization with respect to beta, or the temperature, that is minus 1 over h d squared free energy d beta squared. It's only here where the kink is going to show up. Okay, so again, what this is roughly going to look like, if we plot the magnetization versus temperature, this function has a kink, and the derivative of this function, so here, this is temperature, this is dm dt, this function is going to look like this. So you're going to hit the kink, and then at the kink, the derivative goes to 0. So there's a discontinuity right here. Okay, so now with the magnetization, the discontinuity arises in the second derivative of the free energy. Okay, and so because the discontinuity shows up in the second derivative of the free energy, this is what's referred to as a second order phase transition. Okay, So, in other words, magnetization is a consequence of, or magnetization is a second order phase transition in the alignment of spins in a solid. But now, I mean, if we go back and we look at our, like these free energy functions that we derived, so our free energy function here is this guy. This thing just simply does not have any singularities or kinks or discontinuities in it. This function is just nice and smooth. And what that means is that because this function is smooth and all of its derivatives are smooth, that means that you're never going to see a phase transition from this. Okay, and it turns out that this is a consequence of the fact that it's in one dimension. It's only when you go up to 2 or higher dimensions that when you calculate the free energy in the partition function that you start getting singular behavior. And so now that is what I'm going to show you on Wednesday. So we're not going, so again, we're talking galaxy brain size mathematics here in order to explicitly calculate what goes on in the second dimension in the Ising model. So we're not gonna, we're not galaxy brained here. I'm gonna describe for you an approximation which conveys the essential features of what happens in the second dimension. And so this model is what's referred to as mean field theory. So on Wednesday, we're going to talk about mean field theory of the Ising model in second and higher, 2 and higher dimensions. And I'm going to show you that in 2 and higher dimensions, you do, in fact, get phase transitions. All right, so now we're out of time. We're actually over out of time. I'm over by a minute. So for you guys who showed up late, Wednesday is our last class. We will not have class on Friday, so you can focus on getting your homework done. And that's it. That's it for today. So anybody got any questions? Nope. All right, very good. So that means until next time, stay safe out there, kids. Don't do anything crazy, all right? All right. And somebody says, you too, Chief. Will do, boss. All right. Adios, folks.